And then the third condition was that R out was 0. This is not true. It's R out if you have an open loop circuit device like this is on the order of kiloohms actually. But when you close the loop, it actually drops to milliohms or less. And this is a condition, again, as long as your op amp is happy in its linear region, holds that. And then lastly, we assume it has infinite speed. As soon as there is a change at the input, the output responds. Okay? There is no delay in between input and output terminals. Now, we looked at a couple of circuits with this definition of op amp, with ideal op amps. We looked at an inverting amplifier, non-inverting amplifier, really quickly review them. And notice that this guy can do a lot of amplification jobs that we need. It can give you any gain you want, it gives you zero output resistance, and it can give you any input resistance you want. So it's very, very handy. So the two circuits we analyzed, number one was the inverting amplifier. And we analyzed this circuit by saying that, okay, so in the configuration like that, the voltage on the non-inverting input is forced. Yeah, I'm grounding it, so it's 0 volts. And because I have negative feedback around this device, it's going to mirror itself on the inverting input. So I have 0 volts at the inverting input of this terminal. This is 0 volts. Once I have a 0 volt voltage over there, I can find the current through R1. It's going to be V in over R1, flowing towards the op amp. But because the input resistance of op amp is infinite, because this input current is 0, all of that current is routed through R2 and shows up at the output. So the current is V in over R1, and the voltage drop across R2 is R2 times the current through it, so it's R2 times V in over R1, with a negative sign because I'm pushing the current from the left side of the second resistor, R2. So V out over V in, and if you don't remember that calculation, go and check it. Minus R2 over R1. And input resistance was just R1. So that was one configuration, and we already liked it, but there was a second one which is as useful, and we call this the non-inverting amplifier. So this is RM8 one. And again, analysis is similar. We say I have negative feedback around this. The telltale sign of a negative feedback is that you see a clear path from the output to the inverting input of the op amp. That's usually at least you can assume negative feedback and go on. Yeah.
So I noticed for the first example, you have the inverting on top and the non-inverting on bottom, right?
Right.
Does that matter?
Of course, because if I put the non-inverting input at the top, I will have positive feedback.
Oh.
And none of those nice things happen
No
anymore.
way, yeah.
Right? So make sure you want to have a connection between the output. If it is a direct connection, you want it to be between output and the inverting input. Sometimes you have other circuits in between, can be more complicated, but in general, you want to have a direct connection. In simple circuits, you want to have a direct connection between the output and input. And in this case, because of the virtual short between the two, you have V in appearing across R1. And if you look at this circuit, V in is a voltage division for our V out. If you look at V in, it's R1 over R1 plus R2 times V out. Or you can show that V out is 1 plus R2 over R1 V in. And R in this case for this basic stage is infinite. R out for both of them is 0. So inverting amplifier, non-inverting amplifier, both of them are very, very useful and used all the time. And now today, when we set ideal op amp, what that means is that it doesn't exist. So an ideal op amp does not exist like anything else that put the jacket op ideal in front of it. So today we are gonna go and see what those conditions mean, right? So in real life, what happens if A naught is infinite? What happens if the input current is not zero? R out we don't touch. Actually, that's close to zero for most practical applications. And we also, if you have time, talk about the speed limitations. Okay. So let's go back to one of our op amp circuits. Let's say the non-inverting configuration. Okay? And I'm going to assume that the gain of this op amp is not infinite. So A naught is some finite value. And then I go to solve the circuit. So let's say finite gain. Finite A naught. Let's just call it that. So the effect of finite A naught. How does that affect the performance of my circuit? And I'm using a non-inverting amplifier here as an example. Inverting is going to be the same. Okay, so if I assume the op amp is ideal otherwise, right? So infinite speed, zero input current, and zero output resistance. But by definition, I have this. V out is A naught times V plus minus V minus. So that's the definition of an op amp. And in this case, A naught is not infinite. Looking at this circuit, I can see that the voltage here, the voltage at the inverting terminal, what is it? So I can write it like that from that, but I wanted an independent equation because I want to get rid of the unknowns over there. So I can say that's a voltage division, right? From V out, of V out through R1 and R2. Why can I say that? Because this current is zero, right? It's not drawing any current from that node. So as if it's not touched. If nothing is drawing the current, it's as if it is not touched. So V minus is R1 over R1 plus R2 V out. Okay? And with these two, I should be able to go and solve my problem. I can eliminate V minus from these two equations. V plus is the same as my input voltage. I can find the relationship between outputs and inputs. So if I do that, I have V out equals A naught times V in, or V plus, right? Minus V out times R1 over R1 plus R2. Okay, I'm going to do one thing here. If I divide this fraction by R1, I'm going to have 1 over 1 plus R2 over R1. What was 1 plus R2 over R1? It was the gain of that stage, if A naught was infinite, right? So if you go back and assume ideal op amp, the gain of this stage would have been, let's just call it G naught, 1 plus R2 over R1. Okay? So this ratio here is 1 over G naught. I'm going to make my equations look a little bit simpler. So from here, I can see that V out times, move that second V out term to the left, so 1 plus A naught over G naught is equal to A naught V in. Right? And therefore V out over V in is found from here. or if I divide everything by A naught, I will have 1 over A naught plus 1 over G naught. Right? And G naught is that number. Okay? And then you can see that if A naught goes to infinity, this goes to 0, I will have my G naught back. Okay? So, do I have to worry about A naught not being infinite? Depends. As long as this term is much larger than this term, you don't have to worry about this term, right? So, let's use some numbers. A typical op-amp has a gain of somewhere, the ones that you buy off the shelf in the market, somewhere around, I would say a super high bandwidth op-amp has a gain of 10 to the 4. Typical op-amps have a gain of 10 to the 6 to 10 to the 7. Okay, so let's say 10 to the 6, 1 million, it's a nice one, right? So as long as this gain, 1 over 1 million is much smaller than 1 over G naught, you're safe. How long is that? Maybe up to a gain of 10,000. This is still 100 times larger than that. Even with a gain of 100,000, this term is still 10 times larger than this, right? So even with a gain of 100,000, if you assume A naught is infinite, you only have about 10% error at the end of this term, right? Usually we don't draw a gain of 100,000 from a single stage. So maybe a gain of 1,000 is as much as you push it. You are safe by assuming A naught is infinite for most typical applications. So even with a gain of 10 to the 4, which is some very special op-amps, a gain of 1,000 still means that you're only making a 10% error. Not that much. Okay? So this is not a big deal. We are not too worried about the gain of the op-amp not being infinite. Same analysis, same method shows you that for the non-inverting, for the inverting amplifier, you have the same result. So A naught produces an error of that much. A finite A naught produces a similar amount of error in that stage as well. Short story, I don't care that much about the exact value of A naught. Okay? I'm good. If I'm using something simple, if I'm just trying to, I don't know, amplify a reasonably strong signal from a reasonable source with not so much output resistance, and if I don't need a crazy amount of gain, I don't worry about the absolute value or the exact value of A naught. And actually, you don't find the exact value of A naught in any data sheet. They usually give you a lower bound for it. It's 10 to the 6 or larger, 10 to the 7 or larger. So, for most practical applications, this is not really a big concern. Any questions? Yeah.
So we can use the ideal op-amp equations for like basically any A naught.
To find gain? Yeah. To find gain? Yes. Okay? So, the reason I went through this, it's not a useless effort here. We'll come back to that. We're going to use this result in some other aspect of the typical op-amp. But for calculation of the gain, assume the gain of the op-amp is infinite. And you're safe.
So the larger the value of A naught, the more safe it is to use that.
Yeah.
Okay.
But for most op-amps, you don't really even have to worry about it. Right? So even if you go back to the 60s, when the first semiconductor op-amps were introduced, their gains was 10,000, 5,000, something like that. It just bumped up to hundreds of thousands soon after that and stayed there, or even became larger over time. I don't know where this does this.
Yes, I do. You do. P plus plus B minus that one.
Okay, so finite gain,
So what?
not that much of a trouble.
And that means
Um,
will be minus, because that makes sense. When it's not ideal, then there.
Maybe I should have talked about that
If it's ideal, though,
a little bit later, but let's not worry about that. So,
So then
I'm going to switch to some other topic,
times 2.
and yeah, this I missed at the beginning. So, let's just look at some linear, actually, it's linear op-amp circuits.
Sorry, this is the.
So we saw two
That
ordinals,
is VO is equal to
right? One was the inverting amplifier, one was the non-inverting amplifier. Yes.
Just for the last thing, is that G naught any gain for any circuit that you're analyzing? Or is it just specific to the circuit that?
No, I just called this value G naught.
Yeah. But in the scenario where we're analyzing a different circuit that G naught, like the 1 over A naught plus 1 over G naught having to equal approximately 1 over G naught doesn't hold true. That's only just for this circuit.
Not sure what you're asking.
Uh,
I just, because I wanted my equations to, if you look at the equations in the book, it has all the R1s and R2s everywhere. I just wanted the equation to look a little bit similar. Right? So just define G naught to be that much. For an inverting amplifier, G naught will be minus R2 over R1. But similar analysis.
if we analyze a different circuit, get a different value for G naught, can we still use that same
Depends on the circuit. No, I cannot promise you that. Depends on the circuit.
The bottom one?
No, like not that.
But for most
Because we have VO.
linear circuits, low frequencies, as long as you don't have speed limitations,
Like this part of it.
you can ignore the open loop gain
Because
of
if
fall.
you know,
You can just
is,
assume it is
or
infinite.
is G not bigger than
Infinite,
that?
yeah. So then it's
Okay.
just over.
So linear op-amp circuits, we already saw two.
Then it's just gain.
Let's look at another one. This one is interesting actually.
No, I'm defined it. Yeah.
So that's like V out over V and it's gain. This one's like a repetition. But gain is equal to R. So that's basically gain.
Wait, you just have this here?
So let's look at a circuit like this.
Wow.
And tell me what do you think the output voltage is going to be. Linear, op-amp is happening in its linear region. What do you think the output is? So, if I had only one input, let's say V1, this was my inverting amplifier. I already know it. So it would have been minus RF over R1 for the gain to V1. What is it going to be in this configuration?
So you have two.
E1 R1 plus V2 R2.
Adding.
So that's the difference.
Oh.
There are a couple of ways of looking at it. Right. You can say it's a linear circuit. I use superposition.
Yeah. Equals 1 equals
Superposition, I apply V1, ground V2. Find V out. If I do that,
that's 1 plus.
V out is going to be minus RF over R1 V1. What happens to R2? If I have 0 volts here, what happens to R2? How does it affect my circuit? When I apply V1 and V2, I ground it over here. Doesn't do anything, right? Because I have 0 volts here and 0 volts here. There is no current through this resistor, it doesn't contribute to your circuit, right? So life is easy, that's just it. And then I apply V2, ground V1. Well, a similar thing happens. Okay? And you can add as many of these guys as you want. If you do that,
Wait, can you do this like
that's your output, right? So it's a summing circuit. It's adding all those. Oh, actually, I told you that there are two ways of looking at it. So one is superposition. What is the other one?
Yeah,
Well, we thought about it just like all the currents add
You're gonna
together.
have
Yeah. So the other way of looking at it is to say
You would know.
What I do,
So current.
what the op amp does here is by forcing a 0 volt at this node, it brings all the currents from these branches, add them up, and passes them through the feedback resistor, right? So that's another way of looking at it. You're adding currents, and where do these currents come from? Well, these voltages divided by these resistors. Okay, so you have a summer. You have a circuit that adds analog signals for you. Not only that, you can actually have your own weights. You can add half of this and twice of that and 5 times of this. Whatever you want, right? So RF to R1 is the ratio that you choose for that. So it's a weighted sum. And this is how they had navigation systems in rockets back in the Second World War. You have your feedback system, you have your control electronics, and this is your sum. And so then you have to add different signals with each other. But they didn't have op amps that are made of semiconductors, but you could make op amps out of vacuum tubes. Same idea. They just put this thing into this. But anyway, so it's one building block in analog computers. So you've heard about analog computers. In analog computers, you need to take derivatives, integrate signals, add them up with each other. Those are linear operations. You can also do nonlinear operations. We look at maybe a couple of them later on at the end of the chapter. But for linear operations, this is a fundamental law. So here is one thing you can easily do for this, even if you're not doing anything fancy. If you have 5 sensors and they are similar sensors, what you can do with this circuit is that you can easily calculate the signal out of those 5 sensors. That is an average of the signals, 1/5 of all of those. And the point that in doing that is that nowadays sensors are cheap. But first of all, maybe these sensors are recording different things at different places, so maybe you can have 10 temperature sensors around this room. And you may not care about the individual sensor output. You want to know what is the average temperature in this room. So a circuit like that easily do it for you. But in many other cases, and this might be more relevant to you folks, when you use sensors and you buy sensors, in many cases you're paying for the noise performance of those sensors. So the low noise sensors are significantly more expensive. So if the noise of a sensor, let's say, is 3 times less than the other one, it's probably 10 times more expensive. Okay? But one way to cheat and go around that is to use, if you want to reduce the noise of the device by a factor of n, you add up n squared terms of that signal reported by different sensors. Right? So if you want to reduce the noise in the sensor output by a factor of 3, you put 9 sensors in parallel that are similar, that are cheap, and you average the output of those maps. That drops the noise level by a factor of 3. Right? So a case like this, a circuit like this can do that for you without any digital computation, without needing any further processing, and it is super stable and it never divides by 0. Okay? Alright, so this is one good circuit. Let's look at another one. So let's look at the inverting amplifier again. I have and this circuit we already are familiar with. We know V out over VL. This is minus on 2 over R. Not a problem. We have solved this a couple of times. Okay. So what if I don't use resistors, but instead I use impedances, complex impedances in my feedback loop? So what I can use here is some Z2 and some Z1 here. And if you do that, well, instead of if you use impedances, then you work in Laplace domain, or phasor domain, you can show that V out, let's say in that class, or phasor, which you really like, is minus Z2 over Z1. Okay? Same analysis, right? Everything we said for time domain, you can use the same analysis, same principles here, and you will have that relationship. So let's investigate two such circuits. Circuit 1. I put the resistor for Z1 and the capacitor. Actually, I don't need to call it R1 anymore. A capacitor for the second impedance, the feedback impedance, right? If I go the Laplace route, I can right away see that V out will be in. So S domain or J omega domain is going to be minus the impedance of the feedback element, which is minus 1 over CS over R. Right? Z2 over Z1. And just simplify it. So it is going to be minus 1 over RC minus 1 over S. What does this circuit do mathematically? What is the relationship between V out and V in? 1 over C is a constant. So that's nothing, right? So it changes, there is some factor in front of the relationship between output or an input. But what does that 1 over S mean?
Oh,
Say it again? What is, so if you have 1 over S for a Laplace transform, what does the function? Which function gave you a 1 over S Laplace transform?
Passive. And that's how we did it.
This comes later.
Are you right, Mike?
You remember that?
Yes.
So 1 over S is, if you take the integral of the function, the Laplace transform of that function, the integral of the function will be f of S over S. So what does the function, what does the circuit do? It's an integrator. It integrates your input signal for you. So whatever signal you want to apply to it, doesn't matter. The output is the integral of your input signal. That's great. If you didn't know calculus, all you needed was a function generator and an oscilloscope, and it would solve all your problems for you. Never complain. Right? Never complain. Any signal that the physical signal you apply to this guy, it gives you the integral and the output. No complexity, no need to set your time step, no need to worry about convergence or anything else. Okay, so let's look at it in time domain and see if you can see the same function. In time domain, I go and do my regular analysis. Let's find this current. Okay? And all of that current goes through C. Okay, so when I pass a current through C, V out is the voltage across the capacitor, right? Because this is the voltage, this is the current through the capacitor, this is the voltage across the capacitor. V out is minus Vc. I already know the current through my capacitor. What is the relationship between current voltage of a capacitor? This one you must remember, guys. This is not one of those things that we won't forget. So I use C dV over dt. Right? Basic circuit. start from some time, go to some time, plus some DC naught, right? All of that. Okay? So if I have the current through the capacitor and my output voltage is the negative of the voltage across the capacitor, I can find what the output voltage is. So right away I can see here using this equation is minus 1 over C integral. Let me start from minus infinity so that I don't have to take into account the initial voltage of the capacitor. The current through the capacitor is V over R dt. Or minus 1 over RC minus infinity to T V in dt. Right? Same result. So my circuit is integrating the input signal. Oh, minus infinity is meaningless in engineering. You cannot go back in time, you don't know what happened in really long time ago. You usually start from some zero. We call it time zero, and you measure the voltage across the capacitor at that time, and you need to add it to the capacitor, right? So this is from 0 to T, and VC naught represents whatever voltage you had at the beginning of the process. But it's an integrator, right? Any signal you can turn into a voltage, this can be integrated for you. No problem. Great device. And this is another building block in analog computers. So one difference between when people talk about analog computers for the most part are special purpose. You use them to solve differential equations. Right? You don't use them for machine learning or those kinds of other, or to run Excel or something like that. They're used to solve differential equations. And what you need to solve differential equations is integrators, maybe differentiators, maybe adders. That's it. You definitely need adders, but a couple of integrators and differentiators and adders is all you need. And you can solve any differential equation with any input and any boundary condition after that. And that's how the control systems in the old days worked. You had an analog computer that solved a differential equation that resembled your system, came up with the predicted output, and you tried to correct for any deviation from that.
So what about multiplication?
You don't need multiplication. Multiplication is this. You know, the coefficients are 1 over C's and 1 over R's. So the coefficient, so the differential equation you're solving is not changing. That's the problem with analog computers, that they cannot, if you want to update them, you have to go and take a solving diagram and change resistors and capacitors, right? But so the coefficients in that relationship, you know, same thing with adder. You could add up any number of voltages with any weight that you want, but as soon as you wanted to change one of those weights, you have to go and remove R2 and put something else in place. Right? So it's super fast, it can be energy efficient as well, but it may not be convenient. Right? You don't know, so that's why people use digital computers most of the time. But still there are areas that if you want extreme speeds, extreme performance, you don't have time to do digital stuff. Anyway, so one interesting circuit. Let's keep playing. What if I put the capacitor at the input of my non-inverting amplifier? And same analysis, V out over V in is Z2 over Z1. Z2 is R with a negative sign, of course. And Z1 is 1 over CS. Or minus RCS. And you just had a review of your calculus. If 1 over S was the integral, S is what? Derivative. Right? So the Laplace transform of SFT, sorry, derivative of f some function in time domain will be S times the Laplace transform of a function in frequency domain of Laplace domain. And you can see why that is again. You can look at the current that goes into this capacitor. I in is, by this case, you have a capacitor at the input. The voltage that is applied at the input will change the charge on the capacitor. The current is C dV over dt. So I in is C dV in over dt. But all of this current goes through R and appears at the output as a voltage with a negative sign. So once you have the current, it's easy to see. V out is minus R times the current, C dV in over dt. So this is called the differentiator. Do you know about body plots? You're taking signal course, you must.
In our math courses where we taught there are certain functions you can't differentiate, like if it has a sharp corner. What happens if you put that into that?
Ask it in 5 minutes. Because I want to see if you guys remember. You must know body.
No.
You must know how to plot a function, the magnitude and phase of a function versus frequency. You've done that. Right?
No.
So filters, RC filters, things like that. You haven't seen that.
He skipped it. No, he did skip
You
it.
don't remember RC filters? You have a circuit like this, and the transfer function
I feel like we just learned this.
looks like this.
Yeah, no,
No.
Yeah, no, we don't.
we know the
You know what?
we know the words. We've heard of it.
Words are not- Okay, so then I'll keep it simple. For complex functions, you know complex. You have magnitude and phase, right? So let's say some h of j omega t,
Mm-hmm.
right? You have some magnitude
I know this.
and some phase.
Yes.
Okay, good. So, Bode plot is a plot that shows you how these two change as you change frequency. So you'll see that in control theory all the time, so 100 million times, right? But that's what it is. You plot the magnitude versus frequency and the phase versus frequency. Okay, that's the Bode plot. So, if my function is this, see, if I want to write this in j omega terms, this is 1 over RC minus 1 over RC omega j. Right? Right? For S, I use omega j. So if that's my function, how does it look like when I want to plot the magnitude of h of j omega? Actually, it's not h of j omega, it's just j omega. Sorry.
Yeah.
There's no time, right? So you're assuming that your signal is harmonic. There's no time constant. It's repeating itself. It's only the frequency that we change. Okay, so if my h of j omega is 1 over omega j, how does the magnitude change? Let me here a little bit. So if I want to plot the magnitude of this signal, 1 over omega j. That's my signal, right? So times 1 over RC. 1 over RC, what doesn't matter, it's just a constant. If I want to plot that, how is it going to look? It's just 1 1 over omega j. Okay, so you're right, it's going to have a curve like this, but for body plots, okay, usually this omega is drawn on logarithmic axis.
Oh, so it's a straight line.
Yeah. And the magnitude is also on the logarithmic axis. As you see, you exaggerate some changes, you also some other changes. So it's going to look like this. Right? Straight line. You double the omega, you double the frequency, your amplitude goes down by a factor of 2. 10 times the frequency, amplitude goes down by a factor of 10. Right? So that's what it means. Straight line going down. So what does this mean in terms of function or operation for an integrator? An integrator gives more weight to low frequency signals, and high frequency signals are basically attenuated, or maybe not amplified as much.
And the weight is like associated with like high frequency as well, right? So it's like affected by the filter as well.
So it's what the way that we mentioned before, that when you want to reduce noise, what did I just tell you? That I told you, check, you add up that signal over, you average multiple of them, right? If you consider noise to be a high frequency signal, by passing a noisy signal to an integrator, you integrate the noise component. Your signal is the low frequency component, right? So that goes through with some gain, but the noise will be attenuated. You reduce the noise by using integrators if you know why the phase shift is caused, right? That's for an integrator. How does it look like? The same amplitude versus frequency graph. How does it look like for a differentiator? So in this case, it's RC. If I use the omega for S, it's RC omega J. This is the magnitude of RC omega J. Right? I put the RC out. So how does it look like? Straight line going up if this is logarithmic, right? If I choose logarithmic axis for both, it's going to look like this. Right? It's some slope. The slope is from RC. But double the frequency, double the signal. Right? For the same RC value, same input signal amplitude. Going back to the noise issue that we just mentioned, what happens here? If you use a differentiator in front of after a noisy signal. Considering that your signal is probably low frequency, let's say sensor signal, and noise are these spikes that we see on the oscilloscope if you use closely enough. High frequency, there are a bunch of them. It amplifies noise, right? So you pass a noisy signal through a differentiator, things get much worse. You will have a much noisier signal at the output than the input. For that reason, we don't like differentiators. Right? So we almost never use differentiators because they increase the noise of the signal. Noise is the unwanted part. You don't have any way from it. It's physics. It's real world. Noise is always coming with your signal. And unless you have a super strong signal relative to noise, you don't want to increase noise. A differentiator will increase noise. It amplifies noise that comes with your signal. That's, in most cases, something we definitely don't want. So for that reason, we don't like differentiators that much. Mathematically, this is perfect. Actually, if you go to the lab and get that circuit on the breadboard and apply 1 volt sinusoidal or 1 volt square wave or 1 volt rectangular wave, triangular wave to this thing, it takes the derivative for you beautifully. But drop that amplitude to a millimeter or 0.1 millimeter. And same amount of noise, all of a sudden you see that the signal is lost at the output of the differentiator. Now coming back to your question. You know what, let me not come back to your question. Let's just use this two circuits in a couple of cases. So let's say integrator circuit here. And you apply the square wave to this thing. If you guys have the time, so in your last lab, there is a section that I think it's a bonus section now, that we want to use an integrator or engage an integrator. Just do that part and then see this stuff on the oscilloscope yourself. You're applying a square wave to this integrator. What do you think the output will look like?
The average of
Say again?
Integrated, it's like soft.
So for, let's say, this portion of the wave from 0 to T1,
Oh, the one.
you're applying a constant voltage to your integrator. So what is the integral of the constant voltage over time?
Zero.
It's just T times some constant coefficient. So the only thing to remember is that the gain of an integrator is negative. So you're going to have something like this. So let's say if this has been going on forever, you're going to have something like this. And then as soon as the input voltage becomes negative, it goes up. Down, up. And so on and so forth. Right? If you start from 0 volts, you need to give it some time until it becomes stable, no initial voltage and everything else. But if it is running forever, this is what you get. What happens if you if you apply a sine wave to the input? You get a cosine. Depending on the frequency, you have that omega factor in front of your cosine, right? So 10 Hertz signal, the 10 Hertz sine wave goes through it, let's say, with an amplitude of 1. 100 Hertz sine wave goes through it with an amplitude of 1 or 1/10 of that, right? But you have that 1 over omega in front of it, a phase shift plus a change in amplitude. That's what we expect. What happens if you apply a ramp? That signal that you have, the ramp that you have over there. What happens if you have another integrator after this and you apply it to the input of that?
The capacitor charge is charging.
You get a quadratic signal, t squared, right? And t cubed and all of that. So you're going to have something like this. It's going to look like that. It's a bunch of quadratic waveforms I'm talking about. Looks like a sine wave, it's not a sine wave.
Oh.
But if you look at the difference between this and sine wave, I think the difference is about 4%. The amount of current power is about 4%. So this is how the chip function generators in the old days produce sine waves. Producing a sine wave actually is not an easy thing. That's a proper sine wave. So in the old days, the chip function generators that you bought, they would produce a square wave. From that, they would integrate it and get a ramp, and integrate that and give you a sine wave. Okay? But it wasn't a sine wave. It was 4% difference. To your eyes, it was better than the function generators we have in this time. These ones are just crap. Okay? And then similar thing happens or the opposite thing happens if you apply these signals to a differentiator. Right? You apply that quadratic waveform, you get a ramp. You apply your ramp, you get your square wave, right? Same here, if your V in, V out. So you apply this to the input, you get, again, remember, the gain is negative. no delay here, so it's supposed to go after. Okay. You apply a ramp, you get the square wave at the other. What happens if you apply a square wave to a differentiated ramp? Back to your question.
Nothing. Straight nothing.
What happens? What is the derivative of the square wave?
Nothing.
Oh yeah,
it's just
You get a bunch of impulses.
yeah.
Oh.
Okay? Now, the difference here is that between these impulses and the real impulse is that the amplitude of these guys is not infinite. So if you assume ideal op amp with infinite speed and everything else, yeah, it's an
Yes,
impulse.
makes so much more sense.
Real life op amp, you're limited by the power supply, so this should hit the power supply limit and then come back. But that's what you will get, a train of impulses. Real life, however, you don't have square waves with a 90-degree transition. It needs a little bit of time. So that gives you time to make an impulse with non-zero wave. Right? But that's how you can make train of impulses if you want. Let me see.
He's still much more than our copy. Yeah, he explained something for us, and it makes sense.
Okay, so let's stop here for a break, and you can come and pick up your papers.
Alright, time to be sad. My heart is ready. Let's go, 1 and 0. I didn't get 0.
Simmer!
We'll take that. It's not 0. We'll take that.
You didn't
Yo, why is there just a bonus?
Let's go! 30% baby!
What? Fuck you. Hero. Fuck you. No, right? What? You are the 1% that got it. He said, what? Congrats. I got 90.
What?
Not even in here, bro?
John, you're just gaslighting yourself.
I just get a bonus here.
I got bonus too. I got bonus. We do a ticket. I got 3. What's up, mine?
I'm not a 0.
Not a 0?
Not a 0. Matthew. How'd you do?
It's a competition to see who got lower.
I got 90%.
Not good, bro.
Peru. What star tag did you have? That's
But it's at a 40 mark. Oh, yeah. 3.5.
Yeah. 6 plus 6.
Oh, sorry. This is another addition.
Oh, okay.
So I still feel you got
Look at that. Nothing answered. 10 out of 10.
I'll message him.
It doesn't matter.
Oh, because you have access to it, buddy.
What?
You have access to it.
No, I didn't solve for it. They give me 4 out of 4 for not solving for it. But like I knew the process, it's just I ran out of time, right? Yeah. Yeah. But yeah, like I had all of my methods down and I got very close to solving it, but then I just ended up at like this shit and had to solve for V out over V in and but like yeah.
My method's just not right.
Actually, I'm surprised I did that. It's almost 50%, and I was at 50%.
That's crazy.
I think it's just hard to get through like, hey, the assignment was
Thank you.
Bro, I got the second one.
Okay.
Oh, if you want Kendall, you're fucked.
Let's get back to our lecture. Alright, so we saw a bunch of circuits, linear circuits with opposites, and again, as I said before, know your op amps, you're safe in 80-90% of situations that you have to deal with in analog electronics. I'm talking about op amps. So, we saw the linear circuits with op amps. Ideal op amp is a fantastic device. The challenge is that it's an imaginary device. It doesn't exist. Okay? So we looked at what happens if A naught is infinite. And for the most part, it seems that it doesn't bother us much. If A naught is not infinite, if it is a million instead of infinite, for reasonable gains, I'm okay. So that condition, not a huge deal breaker. But let's look at some other non-idealities of options.
What's your?
So the first one is finite gain must be covered. Must be okay. Right? Second non-ideality of an op-amp is that input offset. What does that mean? It means that if you short circuit the two inputs of an op-amp, by definition, you expect the out to be 0. Right? But for real op-amps, it's not 0. So let's say you short circuit the two inputs of the op-amp, you measure a few millivolts at the output. Okay? So that's called offset voltage of an op-amp, input offset voltage. And it is modeled by adding the voltage source in series with your usually non-inverting input. You can add it to the inverting or non-inverting input, doesn't really matter. The offset voltage is not a fixed voltage for a group of op-amps, right? So you go and look at, let's say, 741, the input offset voltage is stated to be 1 millivolt. That's it. Okay? And you look at the different op-amp, let's say OP66, and it's 100 microvolts. But it's a statistical number. It's going to change from op-amp to op-amp. It may actually change over time for an op-amp. But for the most part, it's relatively fixed once you pick your op-amp. And for that reason, you can account for it in a few different ways. But so VOS, the offset, is a random number, can be positive or negative, and usually you have a bound for it. Okay? So it just tells you how good that offset voltage is seen in the data sheet. It tells you how good this op amp is in terms of having an offset that is close to 0. But what the actual value is, you don't know. You have to use that op amp, you have to test that op amp to figure it out. Where does it come from? It's from the mismatch between the transistors that you have at the input stages of these op amps, especially the input stage. Remember, we looked at the input circuits of the few op amps. They all had 2 transistors at the input, emitter coupled or source coupled most of the time. And these 2 transistors should behave the same for the 2 inputs. There is a tiny difference between them. 1% is too much, maybe 0.1% difference between these 2. Beta of one may be 300, the other one may be 302, right? And that small difference, as the signal, as that tiny difference goes through the high gain of the amplifier, adds up and shows up as an offset voltage at the output of an op amp. In many cases, not a big deal. A couple of millivolts doesn't kill you. In some cases, it can actually be the end of the circuit. So let's just look at 2 examples here. So let's say I have an op amp with a nominal offset voltage of 1 millivolt. It's a typical op amp, right? And I want a total gain of, let's say 10,000 or 100,000. From these op amps, I use 2 op amp stages, let's say each with a gain of 1,000 to amplify this signal with a gain of overall gain of 1 million, right? So let's say 1 million overall gain. So let's say AV total is 10 to the 6. Okay? So what I do is that I choose, 999 R here, and R, and then R, 999. Right? Because this is a non-inverting stage, the gain is 1 plus R2 over R. So that gives me gain of 1,000, gain of 1,000, and life should be easy. But if the op amp has an offset, or is said to have an offset voltage of 1 millivolt, with the gain of 1 million, you're probably looking at a signal with an amplitude of microvolts, right? So your power supply is plus or minus 10, right? So plus 10 and minus 10, plus 10 and minus 10. And you're amplifying the signal on the order of microvolts. It can come from a thermocouple, for example. The thermocouple produces microvolts per degree centigrade in typical situations. So this is realistic. A gain of 1 million may be needed in some cases. You make this, and what do you think is going to happen? Your second stage is most likely going to be saturated, right? Why? Because if this guy has a millivolt of offset, add that 1 millivolt of offset here, that 1 millivolt of offset with a gain of 1,000 becomes 1 volt. And 1 volt with a gain of 1,000 here becomes 1,000 volts. But your supply is only 10. So this second op amp is going to be saturated, right? And you really have no way of fixing it. So can be a bit of problem, a big problem. Another place where the input offset voltage is a major pain is when you make an integrator. We saw that we don't like differentiators, we would like to use integrators instead. But if you make an integrator and you have some offset voltage here, you have your offset voltage here. What do you think is going to happen? You have a signal coming in that you integrate and everything is nice and beautiful. And you have this VOS, this offset voltage, that you also integrate. Right? So the problem with integrating this signal is that it's a DC value. So it's going to be 1 millivolt times T. So it's going to ramp up, and at some point your op amp will saturate. And that's it. It will not. So it's going to be a superposition between your input and this guy. But depending on how big this guy is and what is your integrated gain, integrating the DC value creates a ramp upwards and downwards depending on the side of the offset voltage. But it goes up until you hit the power supply, the maximum output voltage you can have. And after that, your op amp is saturated, it's not doing it anymore, none of the good things that we wanted are going to happen. So again, a big problem here, right? So how do you fix that? Most of the time you can't. Most of the time, when you get an op amp, the offset of that op amp, it is what it is, right? So, my recommendation, if offset is the problem, go and find a different op amp. There are op amps out there that have sub-microvolt offset voltages. Okay? And they do it through different ways. There's post-fabrication trimming, there is switching techniques, all these different techniques. But they can give you sub-microvolt offset voltages. If offset is really a big problem for you, go buy a better op amp. Invest in money to buy a better op amp. Because if you buy a bad op amp, let's say an average op amp with a few millivolts of offset, and you fix it, because some op amps actually, what they do, and 741 is one of them. When you buy the op amp, they have 8 pins, they come in these 8-pin packages, and they give you actually access to 2 pins that you can use to go and make the offset 0, if you really want. Right? So you play with the voltage between these pins. Each op amp is slightly different, but usually you have access to 2 pins to go and make the offset 0. You can do that, but your next circuit will have a different offset voltage. The op amp is different, the offset value is, for the first one is 1 millivolt, for the next one could be 0.7 millivolt. Now for the other one could be minus 0.2, right? So that you can do if you really have to, and if you're making one circuit, or if you can pay for calibration of your circuits. Better solution is to just go and buy a better op amp.
How much money does it take to get one of those microvolt?
Not that expensive. So low frequency, so if 741 is, I don't know, 50 cents, those are like $1 or $2. They are not that expensive. But if you're pushing, if you're so sensitive to that offset, you're probably dealing with a problem that is worth investing that bit more money into getting a better component. Okay? So my advice, don't bother with if you can. Sometimes you can't. Sometimes you have the best op amp there is and you still want to get rid of the offset, so you have to come up with a solution. But for most typical applications, I'm not like that.
How does having any offset not make the integrator obsolete? Because even if you have those micron volts, it's still going
I'll come back to that later.
ramp up and ramp up.
Yeah, we'll come back to that.
It's like it's just going to be an extra 1,000 T.
Do you see a problem with the basic integrator I showed you? There's a big problem with that circuit. Make that circuit in the lab, it will not work. So we'll come back to that. Finish. Okay? But the solution I have for that will solve the offset problem as well. Anyway, so if you want less offset, buy a better op amp. That's your solution. Next problem. Next non-ideal behavior from op amps. We said these input currents are 0. In reality, they are not 0. If you again check, remember the circuit for an op amp, you're going into the base of an op amp, of a BJT. I think I even have the case still open somewhere. Yeah. Okay? The signal is going into the base of your BJT. If I'm biasing that BJT with a 10 microamp current and my beta is 100, it's still a 10 nanoamp current. It's not zero. Sometimes 10 nanoamp is a lot of current. Some other cases you may go into the gate of a MOSFET. Fine, the gate of a MOSFET should not draw any current. Well, the problem is that you do not have access to a gate of a MOSFET because, again, we said before that you have electrostatic discharge issues if you go directly to a gate. So usually there is protection circuit at the input of those MOSFETs. And that protection circuit draws some current. So therefore the current of that input, of that, even a FET input op-amp is not zero. But this is all relative. So for some applications, 1 nanoamp is zero. For some applications, you want something that's a 1 picoamp is zero, or 1 femtoamp is zero. There are op-amps out there that have input currents on the order of femtoamp, right? So what does that mean? So it means that if you have a 1 picofarad capacitor, that's a small capacitor for most applications. If you have 1 volt on that, and you want to measure that 1 volt with your op-amp, it takes 1,000 seconds for that op-amp to discharge your capacitor. You have plenty of time. Okay? So pick that up instead of the one. If you use a 1 nanoamp input current op-amp, it takes 1 milliseconds to discharge that capacitor. Okay? So look at your application. If you don't care if your microamp is the same as zero for you, almost any op-amp can do the job for you. If you have to be careful, if you're talking about nanoamps and picoamps, go and select your op-amp carefully. New op-amps are mostly based on MOSFETs or JFET. Well, there are some JFET input op-amps from the old days, there are some new ones. There are a lot of MOSFET-based op-amps. MOSFET-based op-amps usually have picoamp and less for input currents. BJT op-amps, the old guys, have microamps to nanoamps for your input current. But microamp is a really old, outdated design. Now, again, my recommendation, if you want, if input bias current is a problem, go and buy a better op-amp. There are thousands of them out there. Go and buy a better op-amp, right? But if you want to compensate for the effect of input bias current, what you can do is that you can, you know the values, because the input offset, the current that goes, sorry, not the offset, the input bias current, the input current of these op-amps is the base current of the 2 input transistors, for example. You know the bias current, you design the op-amp. It's 10 microns, let's say, the bias current. Divided by the beta of the device, it's 10 nanovolts. This is relatively well defined. And the direction is definitely not random. So when you talk about the input current of the op-amp, the value is more or less whatever the manufacturer tells you, and the direction is in or out. It's the same as whatever they tell you. So because it's well behaved, you can compensate for it. You can come up with circuit techniques to zero out the effect of input offset current on your output. I wouldn't bother. Just go and buy a better op-amp. Nowadays you don't have to. If you have to solder 3 extra resistors on your board to take care of the input bias current, or just buy better op-amp. Fewer components, fewer assembly, fewer chances of things going wrong, and you probably are dealing with a better op-amp. Anyway, one thing that may cause a little bit of problem is that these 2 currents are not exactly the same. So there is an offset between the 2, but let's not worry about that. If your current is picoamps, the offset is probably femtoamps. Okay. So, 2 easy solutions for 2 big problems. If you have offset voltage problems or input bias current problems, buy better op-amps. Easy solution. If you're not making a million of a circuit, the cost is negligible. Right? So if you're making 100, 200, 500, the engineering time that the employer has to pay you to fix all these issues and troubleshoot them and then go through revisions and everything else is worth more than 1,000 times $2 in extra cost of you. So don't even bother. Now, this one is series. So we said the op-amp has infinite issues right away. Nothing in nature has infinite speed. Even not. So, by design, when the manufacturers design op-amps, the circuit designers design op-amps, these are complex circuits, but they design them such that the transfer function, that A naught that we have, instead of being a constant over all frequencies, which is impossible, is something like this. So the A of, let's see, S in the Laplace transform, the postulate is some A naught over 1 plus S over some Q naught, or just something like that. Okay? You know about first order systems, right? First order, second order systems. They make it behave like a first order system. It's like an RC. If you remember the transfer function for an RC circuit, it's the same thing, 1 over 1 plus S over omega naught, right? That's it. The only difference is that this has a gain in the numerator. So, if I plot that function, and you already know how to do that, if I look at the body plot of that, so that's the log of omega and the magnitude of this function, this is how it looks like for a real op-amp. You have a fixed gain at low frequencies. If you know what I mean by S, right? Yeah, S is j omega. Okay, so S is j omega. So or you can write this, if you think about j omega, is A naught over 1 plus j omega over omega. Okay, so as we change the frequency, if this speed, this function will change, right? Super low frequencies, if omega is much smaller than omega naught, this term is negligible, right? And you have your, so this is like 20 log. This axis is also the rate. So you have a constant value, right? Let's just say this is logarithmic. So the logarithmic axis, you get a flat line. The gain is not changing with frequency, as long as your omega is much less than omega naught. Once you hit omega naught, what happens? We drew it like this. In reality, what happens is you're going to start to slowly drop. The amplitude slowly drops with frequency. If you go far away from omega naught, if omega is much bigger than omega naught, then 1 is negligible. The amplitude drops directly with frequency. 5 times higher in frequency, 5 times smaller in amplitude. That's a first order system. And you get a straight line here on a log axis. Very low frequencies, that's what happens. At omega naught, what did we have here? You should remember some of this stuff. What was this difference between the theoretical super low frequency and actual value? That's your 3 dB corner frequency, right? Why? Because if omega is equal to omega naught, this magnitude is 1, this magnitude is 1. The complex magnitude is square root 2 times less than the low frequency value. The power of the signal is half. Right? V squared is half. So it's the minus 3 dB corner frequency for your signal. usually made our lives easier and just drew it as a straight line up to here and then straight line down. But in reality, there is a transition, right? So you go from a fixed gain at low frequencies, slowly transitioning to a direct drop with higher frequencies. Okay? So this is how an op amp behaves. Right? Very low frequencies. So ideally, the ideal op amp would have a straight line all the way to infinite frequencies. But in reality, we make this much. We get this. So we know the A naught value. A naught is 10 to the 5, 10 to the 6. What do you think the value of this omega naught is? Forget about radians per second. Let's say in hertz. For a typical op amp, for a normal op amp.
Why?
It's 5, 10 hertz.
Oh, really?
Right? It's 5 hertz or 10 hertz. So if you have an open loop op amp and you want to amplify a signal with it with the maximum gain, you can only do it up to about 5 hertz. After that, the gain starts to drop. Okay? What a disaster. So op amp is great as long as your frequency is less than 5 hertz. No. Let's see what this does to our circuit in a typical configuration. That's a non-inverting configuration. Okay. We analyze this with finite gain. This was the relationship between output and input. If I didn't have any, if I did it in time domain, all resistors, no capacitors, no time dependence. If my A is complex, I can still do the same analysis in phasor domain, right? Or Laplace domain. I just have to replace this A here with its complex form. So let's just do that. Let's cheat. Use this at the bottom and save ourselves a little bit of money, a little bit of time. Time is money though. Okay, so this was in time domain ideal op amp. In this case that I have phasor domain and then my op amp has speed limitations. And then remember that G naught for this circuit was the gain of the circuit if the op amp was ideal, 1 plus R2 over R. That's the gain of, that's the definition of G naught. So if I write that, if I know that A naught, instead of the fixed gain, I have some A of S that looks like this, some A naught over 1 plus J omega over omega naught. Right? This omega naught is the first pole of the op amp. So if I plug that into that equation, I get this relationship. So 1 over G naught plus 1 over this expression. So 1 plus J omega over omega naught divided by A naught. Okay? So let's just play with this in a little bit. It's going to be multiply everything by G naught for now. Oh, just one more thing. In this kind of a situation, you know, what do you, so this 3 dB, I'm sure you've heard about it. You have, right?
Very briefly.
Once from
You have. How much there is to explain? 3 dB. So, when you plot these on frequency plots like this, have you heard about 3 dB bandwidth? Oh, you're going to hear it a lot. But that's what it is, right? So, you may have a lower end to your frequency response. It could be another 3 dB drop over here, another 3 dB drop over here. The difference between those are your 3 dB bandwidth. In this case, I don't have a lower end, so it goes from DC to this frequency. That's my bandwidth, right? Why do I call it the bandwidth of my circuit? Because after that, my circuit starts to attenuate my signals. I most probably don't want to use it after that bandwidth, outside its operational bandwidth or design bandwidth, right? So that's what the bandwidth means. Most engineering terms, any field, when you hear bandwidth, it is defined based on 3 dB drop, right? Upper or lower corner frequency. That's where your circuit is happy, and the deviation or the changes in amplitude are about 3 dB. Anyway, so this is called the bandwidth of my circuit. Omega naught is the bandwidth of my circuit, meaning that before that, everything is getting amplified more or less at the same gain. After that, my signal is going to get attenuated. I don't want that. So keep that in mind, bandwidth. Now let's go back here. So I have that relationship now, and let's just expand that a little bit. Okay? So this is the real part, the imaginary part. I want to write this as that S over P factor. One, this whole, because this is still a first order system, right? So there is a constant, real constant, and there is a one coefficient of S, right? So this is still a first order system. I want to write it as 1 plus S over P, or 1 plus S 1 plus j omega over the pole of my system. I want to write it in the same format that I had my input gain. The only difference is that this omega naught now is going to change, right? If I do all my calculations over there. Let's see how it changes. So, it's going to be so to have 1 plus j omega over p, I have to factor this part out. Okay? So I factor this part out. All this thing is for a very interesting result. Just bear with me. Okay? So I just factored this term out. I have this left. Now I'm going to start making some simplifications. I know a few things about this often. For example, I know A naught is really large, and G naught for typical applications is significantly smaller than A naught. Right? So if this is 1,000,000, G naught is 100, is 1,000, is 10,000. Right? So I know that. So if that's the case, this I can ignore when I add to 1. And this, I can ignore again when I add to 1. Okay, so what happened? G naught is my low frequency gain, everything works, no non-idealities. I have my first order system, but the pole of this system, where my 3 dB frequency is, it has changed. It was omega naught before, now it is A naught omega naught divided by G naught. Right? So let's just use some numbers. If A naught is 1,000,000 and G naught is 100, right? And omega naught was 10. We can open loop op amp, that frequency was 10. Now that I have closed the loop and I'm drawing some gain from this guy, the pole, 3 dB frequency, has moved up to 1,000,000 divided by 100, that's my gain. So 10 to the 4 times 10. It has moved up to 10 to the 5. Right? So if I go back and plot that gain relationship on this curve, you'll see that it has actually moved up and goes down over there. So I'm not telling you why I'm drawing this, but at any gain, so this is your G1, let's say this is your G2, at any gain, this is going to happen. You're going to move that pole from the original omega naught at the beginning to some much higher frequency. How much higher? It's A naught omega naught divided by G naught. Right? This is your new pole. Okay? This is your new bandwidth. So what does it tell me? If I had an op amp with a corner frequency of 10 Hertz, with a gain of 1,000,000, if I make a circuit with this, I can only amplify signals that are up to 10 Hertz with that thing. After that, the gain starts to drop. But if I use that same op amp with a gain of 100, all of a sudden, my corner frequency becomes 100 kilohertz. So I have a flat gain all the way to 100 kilohertz. Right? Hold on. Okay? Now, so this is my new pole. Let's just call it, what do we call it? Omega 1. Okay? Another interesting factor here. Look at the product of this new pole, which is A naught over G naught times omega naught, and the gain that I'm getting out of this circuit. So the product of my gain G naught times the pole that I have now, the bandwidth of my circuit now, A naught over G naught times omega naught. This is my new pole, right? If I multiply these two by each other, G naught cancels, and I have a constant number. This is called the gain bandwidth product for an op amp, right? It's constant. Once you buy an op amp, that's a constant number because omega naught is set by design, A naught is set by design. It's constant. How do I use this? What is the point of this? Well, it tells me that if you want whatever gain out of this, I can use this equation to figure out what is my working bandwidth, what is my operational bandwidth out of this. So if you want to amplify, let's say, an audio signal that has a 20 kilohertz bandwidth, you say, okay, so my omega is 20 kilohertz, my gain bandwidth product for this op amp is 1 megahertz. Right? So why is it 1 megahertz? Because A0 has no units. And this one is hertz or radians per second. So if the gain bandwidth product of my op amp is 1 megahertz and the signal frequency or the bandwidth that you need is 20 kilohertz, right away you have a limit on the maximum gain. Right? 1 megahertz on one side, 20 kilohertz on this side. It means that the maximum gain, closed loop gain, G0, that you can get with this op amp is 50. Right? Anything more than 50, it may, your high frequency signals may be attenuated. So that's the gain bandwidth product. So this is a speed limitation for op amps. This is a linear limitation on speed. There is a non-linear limitation on speed as well. I'll talk about it in the next lecture. But so gain bandwidth product is really, really important. This one you cannot go around. You can still buy op amps that have higher gain bandwidth products, but it's a real limitation. So if you buy the best op amp your money can afford it, you still have this limitation. It may not be a problem, because nowadays you can have op amps with gain bandwidth products of gigahertz, right? But it's going to be a limitation on how much gain you can have and what is the maximum bandwidth you can have from this op amp. So this one is the one that you have to keep in mind all the time. Input offset current, I buy better op amp. Input offset voltage, I buy better op amp. This one, if you buy the best op amp, you're still limited. And the best op amp is meaningless because best op amp depends on the application. So whatever op amp you buy, this is always a limitation. Okay, so that's that. So a couple of questions, but you guys can address them. We can leave.
You're not here next Tuesday, right?
Next Tuesday, I'm not here. I'll see you on. Oh, you had a question about the quiz. Quiz. The fourth quiz is going to be DC and AC performance of MOSFETs. So both sections into one, 2 chapters into one. And then the quiz after that is just op amps. Okay? I'm going to post a formula sheet for the AC circuits. It's copied from the cover of your textbook. So if you ever opened your textbook, you would have seen it. But I'm going to put it, it's just one page and maybe it's an easy reference for AC circuits. So that
Aiden, run it. Run it.